What if every decision you made created a new reality? What if, right now, there are countless versions of you, each living out different possibilities of your life? Welcome to the world of the many worlds interpretation. In this video, we're diving deep into one of the most intriguing and controversial theories in quantum mechanics, the many worlds interpretation, or MWI. Proposed by physicist Hugh Everett III in 1957, this theory suggests that every possible outcome of a quantum event happens, each in its separate universe. But why is this theory so significant, and why does it fascinate and terrify scientists in equal measure? To grasp the many worlds interpretation, we first need to understand the basics of quantum mechanics. Quantum mechanics is the branch of physics that deals with the behavior of particles at the smallest scales, the level of atoms and subatomic particles. At this scale, the rules of classical physics no longer apply, and instead, we enter a world governed by probabilities and uncertainties. At the heart of quantum mechanics are particles and wave functions. Particles, such as electrons and photons, exhibit both particle-like and wave-like properties, a phenomenon known as wave-particle duality. A wave function is a mathematical description that encapsulates all possible states a particle can be in. Rather than defining a single state, the wave function provides the probabilities of finding the particle in different states. One of the most intriguing concepts in quantum mechanics is superposition. Superposition is the idea that a particle can exist in multiple states simultaneously until it is measured. For instance, an electron in a superposition state can be thought of as being in different locations at the same time. When we measure the electron, its wave function collapses to a single state, and we observe the electron at one specific location. This probabilistic nature of quantum mechanics is a radical departure from the deterministic world of classical physics. Quantum mechanics underpins much of modern physics and technology. It provides the foundation for understanding atomic and subatomic processes, which are essential for fields such as chemistry, material science, and electronics. Quantum mechanics explains the behavior of semiconductors, which are the building blocks of modern computers and smartphones. It also plays a critical role in the development of technologies such as lasers, magnetic resonance imaging, MRI, and quantum computing. The principles of quantum mechanics are not just theoretical constructs but have practical applications that revolutionize our daily lives. Despite its counterintuitive nature, the accuracy and predictive power of quantum mechanics are unparalleled, making it one of the most successful scientific theories ever developed. As we delve deeper into the many worlds interpretation, it's essential to keep in mind these fundamental concepts that form the backbone of our understanding of the quantum world. The many worlds interpretation of quantum mechanics was introduced by Hugh Everett III in 1957. Everett, then a doctoral student at Princeton University, proposed a revolutionary idea that challenged the conventional understanding of quantum mechanics. Dissatisfied with the standard Copenhagen interpretation, which involves wave function collapse upon measurement, Everett sought an alternative explanation that didn't rely on the concept of collapse. His idea was radical. Rather than collapsing into a single state, the wave function continues to evolve, branching into multiple non-interacting parallel worlds. The core idea of MWI is that every possible outcome of a quantum event occurs, each in its own separate universe. When a quantum event happens, such as the decay of a radioactive atom, the universe splits into a multitude of parallel realities. In each of these realities, a different outcome of the event is realized. For example, in one universe, the atom decays, while in another it does not. These parallel worlds are equally real but do not interact with each other, leading to a vast and ever-growing multiverse. A key concept that supports MWI is quantum decoherence. Quantum decoherence explains how quantum systems interact with their environment, causing the superposition of states to appear as a mixture of distinct states. This process effectively hides the interference effects that are characteristic of quantum superpositions, making each possible outcome seem like a separate, classical reality. In the context of MWI, decoherence provides a mechanism for the branching of universes. As quantum systems interact with their surroundings, they become entangled, leading to a split in the wave function where each branch corresponds to a different outcome. Quantum decoherence thus removes the need for wave function collapse and reinforces the idea that all possible outcomes coexist in a multiverse. This interpretation of quantum mechanics offers a deterministic view, where every possible history and future is realized in some universe. However, it also raises profound questions about the nature of reality, identity, and existence itself. By suggesting that countless versions of ourselves exist in parallel worlds, each making different choices and experiencing different outcomes, MWI presents a view of the universe that is unsettling. The many worlds interpretation brings with it a host of unsettling implications that challenge our understanding of reality. One of the most profound implications is the existence of countless parallel worlds. If MWI is correct, every possible outcome of every decision and quantum event is realized in some universe. This means that there are infinite versions of ourselves, each living out different possibilities and making different choices. The sheer scale and complexity of a multiverse with countless branching realities is mind-boggling and difficult to fully comprehend. Beyond the scientific implications, MWI raises significant ethical and philosophical concerns. The idea that there are infinite versions of ourselves living out every possible outcome leads to questions about identity and consciousness. Are all these versions of ourselves equally real? What does this mean for our sense of self and personal responsibility? The concept of multiple, non-interacting selves can be disconcerting, as it challenges the notion of a singular, unique identity. Additionally, the existence of parallel worlds where different choices are made raises questions about free will and determinism. If every possible choice is realized in some universe, do we truly have free will, or are we simply following predetermined paths? The philosophical dilemmas extend to moral and ethical considerations as well. If every possible action occurs in some universe, including those with significant moral consequences, how do we navigate ethical decision-making? The idea that somewhere, in some universe, our worst fears and most regrettable actions are playing out can be deeply troubling. It forces us to reconsider the weight and impact of our choices, knowing that each decision spawns a new reality. Due to these far-reaching and unsettling implications, MWI faces skepticism and resistance within the scientific community. Many physicists find the idea of an infinite multiverse to be overly speculative and lacking in empirical evidence. The notion that unobservable parallel worlds exist challenges the traditional scientific requirement for testability and falsifiability. Critics argue that MWI, while mathematically consistent, lacks the experimental support needed to be considered a robust scientific theory. This resistance is compounded by the philosophical discomfort it causes, as it challenges deeply held beliefs about the nature of reality and our place within it. Despite these challenges, MWI continues to be a topic of intense debate and interest. Its potential to fundamentally reshape our understanding of the universe keeps it at the forefront of discussions in quantum mechanics and theoretical physics. Whether one accepts or rejects MWI, it undeniably forces us to confront profound questions about the nature of existence, the limits of human knowledge, and the mysteries of the quantum world. While the many worlds interpretation is compelling, it currently lacks direct experimental evidence. However, several experiments and observations in quantum mechanics indirectly support the plausibility of MWI. One such experiment is the double-slit experiment, which demonstrates the wave-particle duality of particles like electrons and photons. When particles are fired at a barrier with two slits, they create an interference pattern on a screen behind the barrier, suggesting that each particle passes through both slits simultaneously in a superposition state. When measured, the particles seem to choose a slit, collapsing into a single state. In the context of MWI, rather than collapsing, the wave function branches into different realities, each with the particle passing through one slit or the other. Another line of evidence comes from quantum computing and entanglement. Quantum computers leverage the principle of superposition to perform complex calculations at unprecedented speeds. The success of these computers relies on the reality of superposition and entanglement, both of which align with the MWI framework. Additionally, experiments involving quantum entanglement, where particles remain interconnected regardless of distance, defy classical explanations and support the non-locality aspect of quantum mechanics. While these experiments don't prove MWI, they are consistent with its predictions and illustrate the strange and counterintuitive nature of the quantum world. Despite these supporting observations, MWI faces significant criticisms and competition from alternative interpretations. The most widely accepted alternative is the Copenhagen interpretation, which posits that quantum particles exist in a superposition of states until measured, at which point the wave function collapses to a single outcome. This interpretation has been the mainstream view since the early 20th century and has a strong experimental track record. Critics of MWI argue that the Copenhagen interpretation is simpler and more aligned with Occam's razor, which favors the least complicated explanation. Another notable alternative is the pilot wave theory, also known as the de Broglie-Bohm theory. This interpretation suggests that particles have definite positions and velocities guided by a pilot wave. Unlike MWI, it maintains a single reality but introduces hidden variables to account for quantum behavior. While less popular than the Copenhagen interpretation, the pilot wave theory provides a deterministic framework for quantum mechanics without requiring multiple universes. Critics of MWI also highlight the lack of empirical testability. The existence of parallel universes cannot be directly observed or measured, making MWI difficult to falsify. This challenges its status as a scientific theory, as scientific theories are typically required to make testable predictions. Moreover, the philosophical implications of MWI, such as the existence of countless versions of ourselves, are difficult for many to accept and integrate into our understanding of reality. In summary, while MWI offers a fascinating and mathematically consistent interpretation of quantum mechanics, it remains a subject of debate. Its indirect support from experiments and observations is compelling, but the lack of direct empirical evidence and the existence of simpler alternative interpretations keep it on the fringes of mainstream acceptance. The ongoing discourse around MWI highlights the complexity and mystery of the quantum world, pushing the boundaries of our understanding and challenging our perceptions of reality. The acceptance of the many worlds interpretation could have profound implications for future technological advancements. If MWI is validated, it could pave the way for breakthroughs in quantum computing and other quantum technologies. Understanding and harnessing the full potential of quantum superposition and entanglement could lead to more powerful and efficient quantum computers, capable of solving complex problems far beyond the reach of classical computers. This could revolutionize fields such as cryptography, artificial intelligence, and materials science, opening up new possibilities for innovation and discovery. Beyond technology, MWI has the potential to revolutionize our understanding of the universe in the field of theoretical physics. Accepting the existence of multiple parallel universes would fundamentally alter our conception of reality. It could lead to new theories and models that better explain the large-scale structure of the cosmos, the nature of black holes, and the fundamental forces of nature. MWI might provide insights into unresolved questions in physics, such as the nature of dark matter and dark energy, and the unification of quantum mechanics with general relativity. The multiverse concept could also influence cosmology, shedding light on the origins and fate of our universe. On a human level, the many worlds interpretation challenges our perception of reality and our place in the cosmos. If every possible outcome of every decision and event exists in its own universe, it forces us to reconsider the nature of identity and existence. The idea that there are countless versions of ourselves living out different lives in parallel realities can be both humbling and disconcerting. It raises questions about free will, destiny, and the meaning of our actions. How do we understand personal responsibility if every choice spawns a new universe where different choices are made? Moreover, MWI invites us to think about the interconnectedness of all things. In a multiverse where every possibility is realized, the boundaries between what is and what could be become blurred. This perspective can inspire a sense of wonder and curiosity, encouraging us to explore the mysteries of the quantum world and the nature of existence. It also emphasizes the importance of our individual experiences and choices, knowing that each decision we make is part of a vast tapestry of possibilities. In conclusion, the many worlds interpretation, while still a subject of debate, has the potential to transform our technological landscape, advance our understanding of the universe, and reshape our perception of reality. Its implications are far-reaching, touching on the fundamental aspects of science, philosophy, and human experience. As we continue to explore the mysteries of the quantum world, MWI stands as a testament to the power of human curiosity and the boundless possibilities of the cosmos. The many worlds interpretation of quantum mechanics challenges our understanding of reality in profound ways. By suggesting that every possible outcome of a quantum event occurs in its own separate universe, it raises fascinating and unsettling questions about the nature of existence, identity, and free will. While it remains a topic of intense debate, its potential to revolutionize technology and theoretical physics is undeniable. As we ponder the implications of living in a multiverse, we're left to wonder, what other mysteries lie hidden in the quantum realm, waiting to be discovered? With that said, thanks for watching, and until next time.